Example 17.3. In this example, we consider a double pane window which has a cross-sectional area of 0.8 meters by 1.5 meters. It has 2 millimeter thick layers of glass, and they are separated by 10 millimeters of stagnant air. We need to determine the steady rate of heat transfer through the double pane window and the temperatures in the inner and the outer surface of the windows. The inside of the room is maintained at 20 Celsius, while the outdoors is maintained at negative 10 Celsius. We're going to use the convection heat transfer coefficients as 10 watts per meter square Kelvin and 40 watts per meter square Kelvin respectively. And this convection coefficient is going to include the effect of radiation. We're going to assume that this problem is steady, one-dimensional, and has constant properties. In order to approach this problem, we're going to use thermal resistances. The thermal resistances that we're going to use are going to be Ri, is going to be the convection taking place from the inside of the room to the wall. We're going to have a resistance R1, which is going to be the conduction of the glass. We're going to have R2, which is the conduction of the air. We're going to have R3, which is the conduction of the glass. And then lastly, we're going to have a conduction of the air outside for convection. So we're going to start writing the information. So Ri is going to be 1 over HIA. So it's from the inside of the room. So this part is the inside of the room. And we evaluate that resistance to be 0.0833 Celsius over watts. We notice that the properties of the glass are exactly the same in both sides, the same thickness and the same thermal conductivity. So the resistance R1 and resistance R3 are going to be the same, and it's simply L of the glass divided by K of the glass times the cross-sectional area. This resistance is going to be equal to 0.00427 Celsius over watts. The resistance 2 is going to be the conduction resistance of air. We do not have convection at this moment because it says that it's stagnant, and in that case it will be free convection. So we're only evaluating the amount of conduction that takes place of air. And we simply say it evaluated as LA for air, K of air times the cross-sectional area. And we evaluate this and we find that the resistance is equal to 0.3205 Celsius over watts. And the last resistance is the resistance on the outside, and that is simply going to be 1 over HO times A. And that resistance is going to give us 0.02083 Celsius over watts. So in order to calculate the total heat transfer, rate of heat transfer, we're going to use the change in temperature divided by the resistance. We're going to evaluate from T infinity 1 to T infinity 2, and then we're going to calculate the summation of all the resistances in order to evaluate the total rate of heat transfer. So if we evaluate and we add all these resistances, we find that the total resistance that we have in the system is equal to 0.4332 Celsius per watt. And if we use that value, we find that the value of Q dot is equal to 69.3 watts. Okay, so now let's move into finding the temperatures in the inside and the outside of the window. So we're gonna call this one T1, and we're gonna call this one T2. Then to find T1, we're going to use the same relationship. We're gonna say Q dot is equal to T infinity 1 minus T1 divided by the resistance in between them, which is Ri, and this provides us with a temperature 1 of 14 0.2 Celsius. If we do the same process for T4, actually you could call it T4, so we're gonna go Q dot is equal T4 minus T infinity 2 divided by RO. And then if we do this process, T4 is going to give us negative 8.66 Celsius. So now let's talk a little bit about the results. In the previous example, 17.2, we did the same evaluation but using a single window. Using that single window, we found that the value of Q dot for a single window instead of was equal to 266 watts. So notice that having a single window means that you lose a lot more heat from the inside to the outside, which is significantly reduced by using double pane windows. You also see that the temperature for a double pane window was 14.2. However, in the previous case, when we have a single window, a single glass, we find that that temperature was equal to negative 2.2 Celsius, which means that the temperature in the inside of the wall, so the temperature of the inside of the glass in the close to the room, is significantly higher by 16 Celsius. And if we do the same process for the temperature of the outside, if we find that we found it for a single window, single glass, we found it to be negative 4.66 Celsius. So we do see a considerable difference when we use a double pane window. You're going to have much lower heat of rate of heat transfer, which means that you lose less amount of heat from your room to the environment, which eventually means that you will lose or you will have lower cost in your heating. And notice that also there is a significant difference on the temperatures at the glass surfaces.